Assalamu alaikum. How are you, my dear students? Hope you will be fine and okay. I welcome you all into my today lecture. Like the previous lecture, today lecture is also very important. It is lecture number 31st, the AC through pure capacitor. So let us start with the name of Allah Almighty. Bismillah Rahman Rahim. AC through a capacitor. What does AC through a capacitor means? Before telling you this thing, one thing I would like to tell you right from the start, the few most important point which you should remember throughout your this lecture is this one, that in capacitor allows the flow of current in AC circuit. Yeah, capacitor allow AC while block DC. It has infinite resistance for the DC circuit. In the DC circuit, remember what is its function right here in the DC circuit. Its function is just to store energy in the form of electrical energy, to store energy. Right? In the AC circuit, it store energy, but at the same time, it opposes the flow of AC. So it has a resistance in the AC circuit. For AC circuit, for the AC circuit, it has some resistance. It has resistance, and that resistance we call the capacitive reactance. The capacitive reactance, which I will explain to you in my today lecture, inshallah. So these are the few basic important notes right in the beginning of the lecture. Now let us start that AC through, what does the AC through capacitor means? AC through a capacitor, through a capacitor. Now, when we connect the capacitor within the AC circuit, you see here it is connected in series with the source. Here, this is our AC source right here, which you see. Now, look, we have here this is in fact, if you just put the emitter or place the emitter in the circuit, then I told you that it will definitely describe you the VRMS, right? So this is the, in the circuit actually it will be measured the VRMS, but the equation is for the instantaneous voltage or AC waveform. This is our input here. Now you see that there is the capacitor, and definitely there will be a potential drop across this capacitor, and that potential drop I will label as VC. Okay, now right from the beginning, that if I tell you that look, if we have the two ends of the capacitor, for example the NA and the NB right here. Now since we know that the charging and discharging of the capacitor, the charging and discharging process of the capacitor and discharging process of the capacitor is pure exponential. Exponential. It it does not rise or fall linearly, right? This is in an exponential curve, and if you remember the time when I was explaining this thing to you in the first chapter, and then I told you if this is charge builds up and if this is time, then this is just like this curve, right? And the decay was also exponential. So now you see that, look, right in the beginning, the charge wouldn't build up instantly. The charge wouldn't build up instantly. At time t is equal to 0, at t is equal to, let's say t1 is equal to 0, the voltage across the capacitor will be what? The voltage across the capacitor, this Vc will be 0 when you close the circuit, because the current has to rise, and at that point the capacitor, since its potential difference is 0, so it will not that there will be no current here. Now you see, look, as the time passes, charge builds on the capacitor, and when the charge builds on the capacitor, there might be a time at t2 is equal to t. What happens? The charge is going to build up. Now you see that when the potential difference builds up, and for ideal pure capacitive circuit, there will be a time reached for which the Vc across the capacitor may be equal to the V instantaneous, the potential difference. And at that time, what will happen? That when Vc becomes Vmax, for example, then at that time the current in the circuit will fall to 0. So you have seen that right in the beginning, the current here, the IRMS, or the current in the circuit, is 0. And at that time, right in the beginning, the current I was Imax. It was Imax. This implies this and this implies this. Now let us see that what does this really means. This means that in the pure capacitive circuit, for the pure capacitive circuit, current leads, I leads, I leads Vc by pi by 2, or we can say Vc lags I by pi by 2. So there is a phase difference of pi by 2 between I and V in the circuit. Remember, this V is the potential difference across this. It is not the source potential difference. Here, if you just look to in the diagram, here you have that voltage, here you have the power, and here you have the current. This voltage is in fact what we see, the voltage across the capacitor. So you see that when the current is maximum, here you see that this is your I. So your look here, the current is what? The no, this is the current is not this one. It is the stated like this. The current is this I. So here you see that when the current is maximum, look right at t is equal to 0. This is time, or this is theta also, or both axes. So at t is equal to 0, here you see, look, at t is equal to 0, like if I just see here, look, at t is equal to 0, what happens? I is maximum, as you see. Look, your I is maximum. This one. Your I is what? Your I is maximum, and you see your VC, the voltage or the potential difference, as you see. Look here. Look at this thing. This potential difference is what? This potential difference across the VC. Look, this one. It is 0. Here you see it. Okay, so now they to find this thing, to find the relation between this, or to prove this mathematically, we will both physically, I told you, mathematically I will explain how it leads the current by pi by 2. Yeah, see here, yes, that look, as we know that for the capacitor circuit, Q is equal to what? For the capacitor, Q is equal to C into V. This is V instantaneous. So this implies that Q is equal to C into Vm into sine omega t. That is equal to Vm into sine omega t. Now look, that since that we know that I, or current in the circuit, is equal what? I is equal to delta Q by delta T. So just dividing this by delta Q, you may say by delta T, delta Q by delta T, what I will be writing is that this delta by delta T into what is your Q? It is C Vm into sine omega t. Now you already know that this delta Q and by delta T, it is I. And now since the capacitance of the capacitor is constant, this is the V maximum potential difference, it is constant. So taking this delta by delta T into sine omega t. Now if you apply the limit, you already know that the limit when delta t tends to 0, sine omega t is equal cos omega t. Right? Not interested in the sign here because we say that current is a scalar quantity. Now what we can write here from this equation, that I equals C into Vm into C into Vm into C into Vm into cos omega t. Oh, this one, not, sorry, I'm very sorry. Omega will be taken outside. Okay. So this will becomes equal into omega into cos omega t. Now you already know that this is mathematical function and has no unit. Definitely the product of the capacitance, the maximum voltage Vm and omega, definitely might have unit equal to current, and since this is maximum potential difference in this and this and this constant, so definitely it will be the Im. So the Im equals C omega into Vm into cos omega t, right? Now look, I will revisit this equation, and here I will be telling to you something very special. Here now look, what I can write instead of this, that this Im will be equal to this, Im will be equal to Im into Vm into C omega into cos omega t. So here this definitely tell us that, look, as I told that, now what will be this thing according to the Ohm law, V equals IR, so V by I equals R, or I by V equals 1 over R. So definitely this is nothing but this is a capacitive reactance. So what I'll be writing for this Im VMC omega, what I'll be writing? I'll be writing Vm into Im into 1 over C omega. This is called the capacitive reactance Xc, and this capacitive reactance is equal to 1 over omega C. So we can write that the capacitive reactance Xc, it is equal to 1 over omega C, or we can write 1 over 2 pi F into C. This term is called the capacitive reactance of the capacitor. Capacitive reactance of the capacitor. The capacitive reactance of the capacitor. It depends, this Xc is inversely proportional to the frequency and inversely proportional to the capacitance of the capacitor. So now look, for the DC, F is 0. So what is this X, capacitive reactance Xc? This Xc will be infinitely large and it will resist our block DC. But for the capacitive, for the AC circuit has some frequency. So frequency and the capacitance, and then you have the capacitive reactance. This is why in the AC circuit it resists the flow of AC. So one is this thing. Now revisiting my equation number 1, see here, look, as I told that what I can write, that if I just say look I and FUC, there is C omega and there is Vm and here is cos omega t, right? Now this Vm is the potential difference across the, this is actually the potential difference across the capacitance. Okay, here this Vc, I will write here, this is nothing but it is Vc, and this Vc is equal to Vm in our equation like that. Okay, so you see that look here, this C into this omega into Vm into sine omega t plus pi by 2. This is a mathematical identity that cos omega t is equal sine omega t plus pi by 2. So here you see that I leads V by pi by 2. So this is a kind of mathematical proof. Okay, class, you should not confuse this Vm, as I told that this Vm is what? This Vm is the maximum voltage across this capacitor, right? The maximum potential difference of the across the capacitance. It is not the source capacitance. Clear? So we have one this thing. The next one is the power loss of the let me look for a kind of diagram. Where is the diagram? I will read. Okay. So here you see that look, this diagram is no more required. The difference. Okay. So now the power loss. The power loss in capacitive circuit. In capacitive circuit, here again the power loss is 0. The power loss in the pure capacitive circuit. In the pure capacitive circuit is zero. Circuit is zero. It does not. Why? Because now you see that, look, if you just see for the power, if you apply for the power, look, that when you have I maximum, then you have the V0, and you know that power is equal to what? You know that for the power is equal to what? The power is equal to VI average. Okay, so over one cycle of the capacitor, this power will be what? This power will be zero. So this will be definitely Vm sine omega t, and this will be Im into sine omega t. So Vm Im into sine omega t into, oh sorry, this one is cos omega t. For the I, it was cos omega t. I am into cos omega t because they are out of phase. Cos omega t. And this average value, it is equal to the average of this value is equal to 0. So the power loss is 0. Okay, why? Very simple reason is the reason that IV are pi by 2 degree out of phase. Degree out of phase. What does this means? That if I is maximum, V must be 0. If V is 0, I must be maximum. So you have the power over one cycle. Over one cycle, the power is what? Over one cycle of AC, the power is 0. Okay, so this is the power delivered by the capacitor. Sorry, I'm so sorry. The more conceptually, I would like to tell you that there is no dissipation of heat energy, right? It control the flow of current in a circuit by not the dissipation of energy in the form of heat, rather it stores, and whenever the circuit needs, it feeds it back. For example, let me demonstrate these things to you right over here in a simple way. Look at the graph. Okay, for example, and if we just see, look at this graph, V. So here at this point for the AC waveform, right at this point, the current is what? The current is 0. If I just see I, the current 0 means that energy of the circuit is 0. But at that time, the capacitor comes into action, and the capacitor, which has already stored energy, during this instant, the capacitor starts delivering its energy back into the circuit. So keep the circuits energized, right? So that is all about this. The phasor, the diagram for this, as I already told, that the current leads the voltage by pi by 2. So here I already draw it. Now the next one is the RLC series circuit. The the RC series circuit. Now, what is the RC series circuit? For the RC series circuit, when the in the circuit, like that is that if you have the circuit in which the capacitor, right, and a resistor both are connected in series with the AC source, as I demonstrate here. This is our AC source. This is definitely the VRMS. This is the VRMS. I will use the VRMS. Definitely in the circuit there will be a current IRMS, right? Because the meter always measure the RMS values. So here you see across the capacitor there will be a potential difference. That potential difference is the VC here, and across this resistor it will be the potential drop will be the VR. Here you have the resistance of the circuit is R, and here you have the resistance of the capacitor known as the capacitive reactance Xc. Okay, so in RC series circuit, when R and C, when the resistor and the capacitor are connected in series with the AC source, it is called the RC series circuit. In the RC series circuit, we will calculate the in the RC series circuit, we will calculate the total resistance of the circuit, and we would like to look into this total resistance of the circuit, that whether it is the sum of the XCR or it is what. Look, as we know that from the circuit, from the previous topic, we know that R and I, oh sorry, VR, the VR and I are in phase. The IRMS are, this is I mean IRMS are in phase. They are what? They are in phase. Means that if the current is zero, then the potential difference in the circuit is zero. If the current is maximum, then the potential difference or the IR drop across the resistor is maximum. So they are in phase. If you remember, I told that if this is IRMS, then this will be the VR. So they are all in phase. But right now you have seen that VC and this I are out of phase, out of phase by pi by 2. They are out of phase by what? They are out of phase by pi by 2 here. So now if you just look to the diagram, that diagram is called the V phasor for the RC circuit. V phasor for RC. Here now you just see, look for the V phasor of the RC. What I can write like this. See here. This is the V phasor for the RC. Now look, as I told, this is X axis and this is Y axis. I will not be writing this, but if you remember, I told you that if this is the VR, this is what? This is our VR, the potential difference, right? And I told you the VR and the IRMS, they are in phase, but the VC is definitely what? Out of phase with the IRMS by 90 degree by pi by 2. Okay, this is what? This is the VC here, as you see. Look, clear? Now, what, since we cannot have the sum greater than the VRMS, so definitely if you look here, then this will be what? This will be the VRMS, and this Vrms will be equal to the Irms, right, into the total resistance, the combined resistance of the XC and RC. And that combined resistance we call Z. And later on I will be telling to you that what is this Z. Z is the combined resistance, the combined resistance of XC and RC for RC series circuit. That is the combined resistance. This is called the impedance of the circuit. Impedance of the circuit. The impedance is the combined resistance of what? It is the combined resistance of the impedance is the combined resistance of the circuit. Okay. Now see here that as you see that this is the impedance. Now look, for this we see here, if you just look, this is definitely that the VC. Okay, so now you know that, look, this is 90 degree, so we can easily write that the Vrms equals what? This Vrms in the circuit is equal to the VR square plus the VC square in the circuit, like this one under the root. Or we already know that VC is equal to what? The IR, well, rather write it there. VC is equal to the Irms into XC, where XC is the capacitive reactance or the resistance upper by the resistor. And this is, of course, Irms into R, like this. So instead of this, what I can write, the Irms, yeah, Imax you can write also. The Irms into the R whole square into the the Irms into the XC whole square under the root, like this. So what I can write, this square and this square, it will be taken common and will be taken here, Irms, and this will be equal R square XC square. So here what you see, that the combined resistance is not linearly added, rather it is the sum of the square root of the pure resistance and the capacitive reactance of the circuit. This is called this is called the impedance of the circuit and is denoted by Z to differentiate it from RRXC. And this is equal to R square into XC square. Now let us see some interesting result. For example, if you have a bulb and a pure resistance in the circuit, but if you place capacitor in the circuit, then the brightness of the bulb will suddenly fall. Why? Because the resistance increases. Okay, and another important effect here will be the R square into 1 over omega C whole square. It can be written like this also. And here if you see that if you increase the frequency, right, then the impedance of the circuit decreases. If you decrease the frequency, then the impedance of the circuit increases. So if similarly, if you have a variable capacitor, so increasing the capacitance may decrease the impedance of the circuit, and decreasing the capacitance may increase the impedance of the circuit, and it will affect the brightness of the bulb in this manner if the bulb has some resistance R. Now look for the phase angle. For the phase angle pi, what we can write that this will be equal to tan inverse of the xc by r. This will be equal to tangent inverse of 1 over omega rc. It will be this phase angle. Clear? Power in the AC circuit, power in the RC circuit, power of the circuit. Now for the power of the circuit, power of the RC circuit, yeah, RC series circuit. For the power equation, we can write that power is equal to what? That the power will be written as power is always equal to the IRMS into the VRMS into what? Into the VRMS or the IMVM. Now you see that, look, for the power of the circuit here, you just see, look, what is the VRMS? The VRMS is now not completely along the x-axis, right? For that reason, to find out the power, we will take the component of the VRMS. If I let me see here. Uh, this will be here. Look for the see here. Look, in order to take the power, that is for the power, for power I and V must be in phase, must be in phase. So if I take this angle as pi, then the power what I'll be taking, this is the IRMS. So the component of the VRMS which is along the IRMS, as I told, this is IRMS because it is VR, so IRMS into R. So I will take the component of what? The component of this V which is along I, and this is what? The VRMS x component, right? And that is always equal to the VRMS into cos pi. So for the power, we will be writing power as the IRMS into the VRMS into the cos pi, where this is called the power factor. Is called the term cos pi is called the power factor. The power factor. We call it what? The power factor. So power will be maximum. Power will be maximum f cos pi equals 1. And this is only possible when the circuit behave as pure resistive circuit, circuit. Okay, so this is how the power through the capacitor can be calculated. So thank you very much. I think it is enough for today. So inshallah, we'll see you in the next lecture for the RL series circuit.